Um, it's actually a very exciting time in the technology space, especially in the last 2 years when we have the Gen AI taking the world by storm, mainstreaming in enterprises. We also know that the core of the generative AI is the large language models. But apart from that, there are other technologies which are also shaping the AI landscape. And one of them is the graph AI. So today's topic, in today's talk, I'm going to talk about how graph AI is shaping the AI landscape and what's the future of that in the coming years. So the obvious question to ask is why graph? What is so special about the graph? If you look at the traditional RDBMS, say whether it is an SQL database or a NoSQL database, the data is pretty much living in their own space. They are not connected with each other. Whereas the real world, the data is much more complex. Just to give an example of a social network where people are constantly chatting, passing messages, if you want to understand this system, you need to analyze them in full totality. And graph provides that beautiful template, which has basically two components. One, which is the node where you have, one which is the node where your data lies. It could be anything. It could be from numeric value to text to images to speech or any other modalities. Then we have the edges or the links which connects this data. The figure what is shown there is a very simple form of a graph, but it can have very further complexities associated with it. The graph structure imbues a lot of information to the data, and that allows you to do very complex analysis on your data. In certain problem settings, for example, in case of optimization, let's say if you want to optimize a transportation network, the graph is a natural setting. Given this brief background about the graph, the obvious question is where the graph is getting adopted, the graph-related technologies. One of the first sector which is getting impacted by graph is actually the financial domain. You can imagine the customer, the financial institutions, enterprises, organizations sitting at the nodes, the edges being the transactions happening between them. So several use cases are getting developed, which includes like fraud detection, tax compliances, money trail, insurance, asset management, etc. The other sector which is getting a lot of where the graph is getting a lot of traction is in the healthcare. It includes drug discovery, protein folding, at least at the research level. Graph is getting used even for clinical investigation, for epidemiology, and also for community health. In the e-commerce sector, some of the organizations have already started implementing graph-based recommendation engines. When it comes to telecom and cyberspace, intrusion detection systems, the log analysis, the root cause analysis, these are some of the graph-based use cases. Now, if you look at all these sectors, what I mentioned, they are applying the graph through what is called the graph machine learning. And I'll go a little more deeper into it in coming slide. But if we expand the graph into the knowledge space through what is called a knowledge graph and its interaction with generative AI, then the graph technology landscape expands almost limitlessly. Beyond the current way the Gen AI is being thought about and is being implemented, for example, in conversational agents or chatbots, there is a general question being asked as what is next for the AI. It includes things like, can AI do reasonings? Can one make causal decisions using AI? And that is also actually valid for the graph. And to the next level, if you take, it is all about innovation. Can we do innovation on top of the graph? Those who knows about the OpenAI's 5 levels of AI, they might find this template is very much similar to that. So that's not a coincidence. Actually, it basically tells that the development in graph AI is going to parallel with the development of AI. In fact, there is a symbiotic relation between the two. So let me drill down a little more deeper into these individual pieces of technology related to graph. By the way, the graph, when I speak about graph AI, it includes all the technology which involves a graph in some form or the other. So what is graph machine learning? So one can think about the classical machine learning. You want to do some classification or a regression, right? This is the same happens even at the graph, but you are now doing it at the node level. So you can ask questions, for example, on a financial graph, is a person fraud? And it becomes a classification problem. And when it comes to trying to solve problems at the edge, for example, for a recommendation engine, the usual question to ask is that, will a person buy an item based on the historical, the history of the person's purchase? That becomes a link prediction problem in the graph language. One can also think about whether there is a trend within a cluster of nodes or a cluster within the graph, and that becomes a subgraph problem. And then we can think about the graph itself as one entity and ask several questions about it. For example, in the case of a drug discovery, one would actually represent the atoms as nodes on the graph and the bonds between the atoms as the edges. And then what we do is we actually train a machine learning model which will allow you to connect the molecular structure to its property. Once we have done that, we can always ask an inverse question, is that given a set of properties, can we create the underlying molecules? And that becomes your drug discovery problem. Now, given this machine learning task, the core of that is basically representation learning. Now, what is representation learning? Let's take the example of a node level classification you want to do. You cannot use the graph as it is. We need to break the graph structure. And that is done by this concept called representation learning. So let me give a little more detail about it. So let's take a target node, which is circled there. And we want to find out how can we actually change these features of this node in such a way that it remembers its graph structure. So one of the standard method, which is right now in industry and in practice, is what is called message passing. So what message passing does is the following. It looks at the target node, aggregates the information from its neighboring node at the first level, then goes to the next neighbors, aggregates further the information, and so on and so forth. So each time it aggregates the information, it remembers the graph structure around it. And that's how the final node level embeddings, or what we call, has a memory of the graph structure. So given these basics about graphs, so what are the trends in the graph machine learning? The first paper came around in 2018, what it was called as a graph convolution neural network, and since then the entire field has exploded. There is now a zoo of machine learning algorithms for the graph learning. In recent years, especially in the last 2 years, the transformer has caught attention. The same transformer which is used in the large language model, it is also being applied for the graph. More specifically, there is a model called the heterogeneous graph transformer, which is now kind of considered as an industrial standard for doing machine learning on the graph. There is also, in general, a question about what is next after transformer. This is a generic question even in the AI space. The front runner of the approach which one is thinking about is what is called a state space model. People have already started applying to the this model for the graph. In fact, just a couple of months back, there are a research paper which has appeared where the state space model shows much better performance compared to the transformer, even for the graph-related applications. Then we have the generative graph models, just like your generative models in the language. We also have foundational model for graphs, where we train, independent of the domain, we train a model which can work across. But the jury is still out whether it is actually practical and what are the pitfalls of it. There's still a lot of research which needs to go into that. Then there are these auxiliary technologies which is supporting the graph machine learning and graph AI. They are called, for example, graph compressions and condensation. The idea is that if you have a very large graph, say for example a billion node graph, and you want to actually make it much smaller so that it actually you can do a lot of tasks at the same level of accuracy what you would like to do it on the large graph. The other topics of interest is explainable graph AI, and also how does the graph itself, the graph data itself interacts with a large language model. So these are some of the research trends, what is happening in the graph space. Let me give a very concrete example of a use case. That is what will be of interest to many of you. So here is a problem which was actually solved in my lab. It's a fraud detection on a financial data, which is actually a customer data. It had a 100 million node graph and nearly 200 million edges. It's a heterogeneous graph. In fact, it is much more complex because it has a multi-relation between the nodes. The features sitting on the nodes and edges are very high in the sense that you cannot take that entire graph and the feature and try to put it in the memory. It doesn't fit into the RAM. So how do you actually train a machine learning algorithm on such a large graph? By the way, the figure on the left-hand side, what you see, is only a small snapshot of the large graph. It's only 1 million nodes what is shown there. So the way to solve this problem, what we have created, we split the problem into two parts. We took the graph bare-bone structure, which is much simpler and which can be held into the RAM, and put all the node and the edge features into the traditional RDBMS. For example, it could be a Postgres or an SQLite database. Now, when we want to do the training, we actually pick up the target node, look at the subgraph around it, then query the RDBMS, extract the features, and then pass it on to the machine learning algorithms. And this is done in an iterative sense. Of course, you can actually scale, this algorithm is scalable. What it means is that you can actually apply it even for a billion node graph. But there are certain pitfalls. Most of the computational efficiency is compromised because of the query to the RDBMS and fetching the data from the RDBMS and then pushing it to the GPU. Of course, that is another topic of interest is how do you actually query RDBMS directly from the GPU, not from the CPU. So this brings me to the next topic about what are the challenges of graph ML. So one of the things which I was mentioning before in the previous slide is about message passing. And if you have noticed very clearly that as you try to go further and further deep away from the target node, you have to aggregate information from much larger number of nodes. Okay? Now, in real world, the graph is much more complex. You can have very densely interconnected graph. What it means is that as you go further deeper away from the node, the size of the neighborhood or the subgraph explodes. So you have to aggregate much more information to get a good understanding of the context. The other problem with the real world situation is that the graphs are never stationary. The graph continues to grow with time, for example. And most of these graph machine learning, they are pretty much GPU intensive. So it is also requires sometimes you need GPU even at the inference level, not just for the machine learning training part. Apart from these machine learning related challenges, we also have challenges in when we try to adopt these technologies for enterprise level. One of the basic problem which people do face is how do we actually create the data set, the graph data set itself. It is not easy because you can have data basically spread on different databases. How do you actually bring them together, understand what is the graph schema between the data, and then create the graph structure? Explainability and interpretability is still a challenge. There are already models, but when you think about problems like how one node is connected to far away nodes in the graph, the explainability still requires a lot more work. The issue of dynamic and streaming graph actually adds further level of complexities. And this is also an interesting topic from other perspective, which again, I'll touch in the next slide. So going forward, what is the ecospace for the graph machine learning? There are already standard graph databases. Neo4j is one of the leading vendor for the graph databases. Apart from that, there are certain open source databases like Redis and TigerGraph. These databases, they are known to be scalable, and they provide some functionalities like querying on the database. How do you traverse the database, extract some subgraph, and do some simple questions, answer to some simple questions. But when it comes to machine learning, they have very limited functionalities. There has been some effort to make end-to-end machine learning platform for graph, and they are typically in the academic space and a bit of on the research space. There has been a recent work on what is called a graph storm, which was released very recently. And then there is a platform called AliGraph, which I think is pretty proprietary. Most of these end-to-end graph platforms, they are built on top of open source machine learning libraries for graph, of which the Python geometric or PyG, what is called in short form, and deep graph library is kind of an industrial standard. Going forward, I will now talk about what happens when we think about the knowledge graph. If you imagine the knowledge database connected to the graph structure, it provides much more wonderful opportunities to understand the knowledge, both at the common life level and also at the enterprise level. It allows you to do very fast retrieval of the knowledge, what is required, for example, to do some question answering. It also establishes some hidden relation between the knowledge entities in your system. And most importantly, it's very easy to actually process computationally, and that is what most of the AI algorithms will do at the back end, is to do apply certain computational methods. So let me take a very simple gold standard question answering system, which is the RAG, which is now heavily used in enterprises. So what do we do in the RAG pipeline? You have the data, you chunk the data, create vector embeddings for the data, and you put it in the vector database. Now, in comes the query. You create a vector, you create an embedding vector for the query, and then the retrieval engine will go and search your vector database for those vectors which are very close to the query. You collect all the top K embeddings and push it into the LLM to get a response. Pretty interesting. But imagine that what happens if you connect the graph to it. So this is what my team has developed, a graph-based technique. So apart from collecting the vector embeddings, we also collect the relevant documents, build a hyperrelation knowledge graph, and we prune it based on the query awareness of, based on query, and then push the knowledge graph into the LLM, and it gives around 20 to 25% better performance compared to the baseline RAG architecture. So this, what we call this as a KG enhanced RAG, is today the core pillars of the generative AI offerings from our organization, from some other companies too. So what are the use cases of that? We have shown that this works very efficiently to do question answering on product manuals. Millions of tokens can be easily processed. Log analysis for telecom sectors and root cause analysis. We can also perform a video analysis using the same technology. So let me give a little more detail about how the graph enters the video analysis, or how does the graph enter the vision domain. So if you want to actually extract, if you want to extract much more context and information from the image or from the video, you would actually connect the objects in that through a graph, and then pass the graph into certain algorithms to extract the context, which again then pass into LLM to do some question answering and etc. Because of the lack of the time, I will not go into the details of that. The other topic which is related to the graph is on causal reasoning. That's the next higher level of task which you want to do with your AI systems, and the causal knowledge graph is playing a big role in that part of the space. This is my last slide, and I just want to talk about what's the future of the graph AI. And it is in fact very bright. It's as bright as the AI itself. And if you look at it, many of the topics related to the graph AI is also actually the same as the AI roadmap. In fact, both has a very close relation. In many of these topics, actually, the Fujitsu is working, for example, on graph foundational models, generative graph AI, multimodal graph AI for question answerings across domains, integration of the AI with knowledge graph with other AI technologies, decision making, causal decision making. That's the next generation technology which will appear in the AI space, and I believe that the graph is going to play a big role in that. So that's all from my side. Thank you.